A really common question is to be asked to give a set of quantum numbers from a given electron configuration. So here I've asked a sample question where I say give a set of 4 quantum numbers for each valence electron in sulfur. So the first thing you want to do is come up with the actual electron configuration, and then you got to remember when we ask for the valence electrons, we are talking about the electrons past the noble gas core. The real trick here is we're dealing with 2 different subshells, so we're going to have to deal with them separately. The first one, the 3 S's, remember I always start by considering how many IMSA-bell values we have and to draw a box for each IMSA-bell value. So when we're dealing with an S subshell, we only have one IMSA-bell. IMSA-bell is equal to 0. And in this case, there's going to be 2 electrons inside of there. I always like to make a table to keep track of the electrons, so I always like to list my electrons in a column, and then we have our 4 quantum numbers here to the left. Once we've designated what subshell we're talking about, remember the first 2 quantum numbers, N and L, are given in the subshell type. So we're dealing with a 3S subshell, so N is equal to 3 and L is equal to 0. So L is equal to 0 because we're dealing with an S subshell. In an S subshell, there's only one possible IMSA-bell. IMSA-bell is equal to 0. So for both of our electrons, they're both going to have an IMSA-bell equal to 0. And then we add our 2 electrons into the IMSA-bell box. And really all that we need to remember is they need to be spin paired. Our possible IMSA-best values are plus 1/2 and minus 1/2. All I got to make sure to do is have one going up, plus 1/2, and the other one going down, minus 1/2. So remember, the Pauli exclusion principle says that these 2 need to be spin paired. So one needs to be plus 1/2, the other one needs to be minus 1/2. Then we can deal with the 3p subshell. So we've dealt with these 2 electrons, the 3s subshell. Now we need to deal with the 3p subshell. So we set up a different table because it's a different subshell in itself. Here we have 4 electrons, we have our 4 quantum numbers. When we're dealing with a p subshell, we have 3 IMSA-bell values, minus 1, 0, and 1. As always, the first 2 quantum numbers, N and L, are given in the fact that we're dealing with a 3p subshell. So N is equal to 3 for all of our electrons, and L is equal to 1. And remember, L is equal to 1 because we're dealing with a p subshell. Then we start putting electrons in. Following Hund's rule, the first electron is going to go into IMSA-bell minus 1, and here I have just given it a spin of plus 1/2. That means that the next electron must go into the next IMSA-bell. IMSA-bell is equal to 0, and if the first one is plus 1/2, Hund's rule says that the next one also needs to be plus 1/2. Then when I put in a third electron, it goes into next IMSA-bell, IMSA-bell plus 1, and once again, Hund's rule says that this one needs to be plus 1/2 also. So the first 3 electrons that go in, their IMSA-s needs to be the same. They need to be spin parallel. So now that we have an electron in each one of our IMSA-bells, then we can go back and take the 4th electron and put it into the first IMSA-bell, IMSA-bell minus 1. And because the first electron had a spin of plus 1/2, this electron must have a spin of minus 1/2. So another question says, give a set of 4 quantum numbers for each 3d electron in iron. So same deal, you want to start with the electron configuration. So here's the electron configuration of iron. And even though there's a lot of electrons in there, we are specifically asking about the 3d electrons. And remember, we have 6 of those 3d electrons, or 6 electrons on our 3d subshell. When we're dealing with a d subshell, we actually have 5 possible IMSA-bell values. So it goes from minus 2 to plus 2. And now we're going to put 6 electrons into those 5 IMSA-bell values. As always, N and L are given by our orbital designation. So N is equal to 3 here. And because we're dealing with a d subshell, L is equal to 2. Then I start putting electrons into my IMSA-bell. So the first one is going to go into IMSA-bell minus 2, and I have decided to give it a IMSA-best of plus 1/2. Hund's rule says that we need to put our next electron into the next IMSA-bell value over, and that it has to be the same spin as the first one I put in. So the next electron goes into m sub L minus 1, and it has to have the same spin as the first electron, plus 1/2, so the second one has plus 1/2. So this continues on. The third electron goes into m sub L equal to 0, also spin plus 1/2, then m sub L 1, then m sub L 2, and all of these need to be spin plus 1/2, so they need to be all spin parallel. So we've dealt with 5 electrons. The 6th electron now can go back into the first m sub L, but because there's an electron already in there, it needs to be spin paired. So the first electron that we put in there, I decided to make it plus 1/2, so here the m sub s must be minus 1/2. So we've gone back, put an electron back into our initial m sub L value, m sub L minus 2, and the m sub s must be spin paired to the first electron. The first electron was plus 1/2, so now the electron that's pairing in there must be minus 1/2. So some other kind of questions we can ask in between quantum numbers and electron configurations is, say, what element has 3s1 as its valence electron? So these types of questions aren't that hard as long as you understand that different parts of the periodic table correspond to different quantum number values. So here, because we're dealing with an s orbital, we know that we're going to be talking about an element involved with these first 2 rows. So we're looking for an element in the s block here. So n value starts at 1 in the s block. So this is n equals 1, n equals 2, n equals 3. So if I wanted to have 1 electron in a 3s subshell, it would be sodium, would be the element that has 3s1 as its valence electron. So we do the same thing for 3p1. We're dealing with a 3p subshell, so the p block is over here, and we're looking for n is equal to 3. So remember that the p block starts at n equals 2. This is going to be n equals 3. So this is our 3p subshell, and we're looking for 1 electron inside of that 3p subshell. So in this case, we're going to be looking for aluminum.